Howdy, my name is Sylvain Corlet. I'm the founder and CEO of QuantStack. As an open source developer, I am mostly involved in the Jupyter ecosystem. I am the co-creator of Voila Dashboard and Extensor, and a core team member of CandaForge. I do a lot of work for the community as a board member of NumFocus and the organizer of PyData Paris.
Hi Internet, my name is Johan Mabil. I'm a scientific software developer at QuantStack. As an open source developer, I mostly worked in the Jupyter ecosystem. I've been involved in implementing the Jupyter Debugger. I am the creator of the xeus library. I co-authored Extensor and Xframe, which are C++ equivalents of NumPy and Xarray. I also maintain the bqplot library.
Hello, my name is Mariana Meirelles. I'm a scientific software engineer working at QuantStack. I'm an open source developer. I'm the creator of HyperCytoscape, a graph visualization library, of xeus-sqlite, a kernel for Jupyter, and I developed PyLess which is a tool to help you find deprecation in your code. Prior to QuantStack, I worked at Mozilla and also at the Qt company.
Hello JupyterCon, my name is Martin. I work at QuantStack since 2 years. I work mostly on projects around the Jupyter ecosystem. So, for example, widgets libraries, IPyWidgets, IPyLeaflet, IPyMPL, and bqplot. And I also worked on Jupyter kernels like the C++ kernel xeus-cling and xeus-python, which is a Python kernel that is the backend for the new JupyterLab debugger.
Project Jupyter is the evolution of the IPython project, and the reason for the rename is that language agnosticism is now a key principle in the architecture of design of the project. Looking at the front page of Jupyter.org, you will see many programming language logos, ranging from Python to C++, Ruby, and Octave. All of these languages are now supported by Project Jupyter. The Jupyter name itself is actually the concatenation of Julia, Python, and R, three programming languages popular in data science. The kernel, which is the part of the infrastructure responsible for executing user code, is nothing else but a process implementing a world-specified communication protocol. Implement your protocol once and integrate your language with all the Jupyter frontends, the notebook, JupyterLab, Voila dashboards, the Qt console. Today, there are kernels for dozens of languages, and the kernel protocol is the main extension point to Jupyter. But all these kernels have very different quality levels. How can we help kernel authors benefit from the rich features of the ecosystem?
When authoring a kernel, you have two options to deal with the protocol. The first one is to re-implement the protocol from scratch, but it's not easy. You have to deal with complex concurrent programming models. You have to make use of ZMQ, which is hard to master. You have to sign messages, and you need to implement all message types. Another approach is to reuse an existing implementation, such as IPyKernel or Xeus. Using IPyKernel to make a language kernel has some drawbacks. The first one is that your kernel will depend on the Python runtime. Another one is that the interpreter of your language may not have a Python API. And the last one is we need to export the API of the kernel to the target language for advanced use cases, such as widgets, rich display, and so on. And this may actually be really hard. So what is Xeus? Xeus is a modern C++ implementation of the Jupyter protocol. It enables kernel authors to create new kernels without having to deal with the protocol. Xeus has many advantages over the IPyKernel approach. First one is C++ is a common denominator, so most interpreters are written in C. This makes it easy to embed them. Xeus also provides support for autocompletion, magics, inspection, history, so you can easily write a full-featured kernel with Xeus. And last but not least, Xeus implements the widget protocols. Regarding its architecture, Xeus is really simple. It's made of 4 main components. The first one is a server, which implements the low-level communication layer. The interpreter provides the minimum API you have to implement to author a kernel. The debugger provides the API you have to implement to support debugging. And the last component is the kernel core, which is the mediator component. It's the only one talking to the other. This clean separation between components makes the Xeus library very easy to extend.
xeus-sqlite is a kernel for Jupyter, and some of its features include opening and closing database files, rich HTML displays on Jupyter Notebook and Jupyter Lab, and magics. So let's have a look on some things you can do. Here you can uploading a database using a magic. Here I'm going to create a table, insert some data to it. Now this is the HTML rich display. I can also operate some or whatever other SQLite queries and keywords. There's also quite a few other options that are implemented as magics, as table exists, get info. I can also create a database inside of my Jupyter Notebook and delete it too. For the future of xeus-sqlite, we are planning to integrate it with Vega, which is a tool for visualizing graphs. We already made some tests in the past, and now we have xvega, which is a library that translates the code to C++, so it's possible to use with ease. And the idea is to have all of these kinds of visualizations available to Jupyter users too. Another thing we're interested in doing is porting xeus-sqlite as a standalone application, so it's easier for our users to use it.
So xeus-python now. xeus-python is a Xeus-based Python kernel for Jupyter. It has multiple features, including autocompletion, code inspection, Jupyter widget support, and some magic support. It is also the backend for the new Jupyter Lab Python debugger, so this is a big plus. So let's get started with a demo. So just like any other kernel, when you install xeus-python, it will appear here in the launch page of Jupyter Lab. So if you click here, it will start a new xPython kernel, which has debugger support, and you can start typing code. Okay, so let's continue with this notebook. So this notebook contains multiple demos that I want to show. So first, in order to install xeus-python, it's as easy as running mumba install -4 xeus-python, and that's it. You have xeus-python and it should work. So just like IPyKernel, you can execute Python code, of course. It will always show the latest expression in your cell. So if it's a variable, it will show the variable. If it's a function call, it will show the output of the function call. It redirects streams, so if you print something, it will show on the page. Same for the error output. It supports error handling, and it will show you the traceback. And what is nice with xeus-python is that it will show you in which cell the code comes from and which line. So xeus-python supports code completion. So if you have a very long variable name or function, it will show it to you with tab. Same for the import keyword. It works as well. xeus-python supports code completion, so with the question mark you can show the documentation of a function, or using Shift tab it will show it like that. It has input support, so you can input something. xeus-python also supports rich representation of your classes. So for example, this class has a text HTML representation. So when I create an instance of it, and if I show it in the page, it will show you my rich representation of the class. So as I mentioned before, xeus-python supports IPyWidgets. So you can create, for example, a slider widget. You can get its value from Python. And you can show it multiple times, and of course different views of the same widget are linked, and you can set it from Python. So interact work as well. It supports binary buffers, and you've got high-level widgets library support. So like ITK widgets. It monkey patches the IPython display module. So a lot of notebooks are using this IPython display, and of course it's not IPython, so we don't have it. So we had to monkey patch it to support most notebooks. So you can still use display, just like in IPython, and update display. It still works. You can clear the output, and you have all the display classes that are monkey patched as well. So math, netesh, SVG, everything. So thank you for listening. I leave the board to Sylvain, who will show you interactive C++ in Jupyter using xeus-cling.
Let's move on to xeus-cling. Xeus-cling is actually the very first kernel that we ever developed using Zeus. We had Zeus, which is a C++ implementation of the kernel protocol. What was more natural than writing a kernel for C++ itself? One issue, though, is that C++ is a compiled programming language, and we needed an interpreter. And we found one called Cling, developed at CERN for the root project. But I think I should just give you a live demo. Now is the fun part. So, xeus-cling, the Jupyter kernel for C++, can be very easily installed using Mamba. Just type Mamba install xeus-cling-c counterforge, and it should just be installed, and Jupyter will find the kernel. If you look into the upper right corner of the window here, you will see the C++14 kernel appear. Now, let's start to write some C++ code. So the first natural thing is to have some kind of, hello world example, is to hash include iostream and use stdcout. And you will see the output display in the notebook inline. If you use the standard error output, the same thing will display with some styling signaling that this is an error output. We also catch exceptions and actually show the what error message of the exception. Should you define a variable and just type the name of the variable at the last statement of SOR, omitting the last semicolon, you will see the value of the variable inline in the notebook. Now, like a must-have feature for JupyterKernel is the inline help. For example, should you want to access the std vector help in the Jupyter notebook, just type $std vector, and the system will fetch the documentation for std vector on CPP reference. You can also extend that behavior for your custom types. For example, here I'm typing $xt extensor, and I'm getting the live documentation for the extensor library. There you go. xeus-cling also implements rich data display using the rich display data mechanism of Jupyter. So here is a very simple example of an image class that has absolutely zero logic except for loading an image file into a buffer. And all I have to do for this to be displayed as an image in the Jupyter notebook is to overload the MIME-bundle-wrapper method for that image, and this method will be automatically picked up through argument-dependent lookup. So let's run that code, instantiate an image from an image file, and verify that the image is properly shown inline in the notebook. So rich MIME type rendering, interactive help. Another thing that is a must-have for JupyterKernel is the support for magics. So for example, here I am timing the random shuffle standard algorithm for a vector of size 4, and you get what you expect from the time it algorithm. Now, if you want to do more complex things in the Jupyter C++ notebook, let's check out the extensor library. If you don't know about extensor, you should really check it out. You can find a GitHub repository in the extensor stack organization. So what extensor is, for those who didn't read the documentation yet, it's a C++ library for manipulating ND arrays with an API very similar to that of NumPy for C++. In that example here, I'm instantiating two arrays. One is 2D and the other one is 1D, and displaying the sum of the second row of the first array and the second array. And there you go. You have a rich HTML display of the tensor inline in the notebook. Now, well, you can also define an extensor, 1D array, and reshape it in place and then display it, or even make use of standard linear algebra routines very much in the same way as you would do using the NumPy library in a Python notebook. So in short, xeus-cling provides a very similar experience for C++ developers in the classic notebook as you would get with the Python kernel in the same environment using NumPy and whatnot. Another project that is really dear to us built on Xeus is xWidgets. xWidgets is a C++ backend to the Jupyter Interactive Widgets framework. The GitHub repository can be found in the Jupyter Xeus organization, and it can be installed using Mamba by typing mamba install xWidgets-c kernel to get it from the kernel organization. To define a slider, just include the appropriate header, instantiate a slider, and display it by omitting the last semicolon at the cell. And there you go, you have a slider. By assigning a value to an attribute, you'll see the attribute value reflected in the frontend. You can also access attributes that may be modified from the frontend in the same way. Now, changing some other properties will also have effects in the front-end representation of that object. So yeah, creating visual components from a C++ notebook using xWidgets is now possible, just like in the Python notebook. Jupyter widgets are special in that they have many attributes that you may want to initialize out of order. So we offer a method chaining syntax to mimic keyword arguments in C++. And there you go. We have a slider with a set description and min and max values centered on 0. Should you want to include or create a button widget, just include the appropriate header. Now we will link the clicked event of the button with a custom callback that just prints to the cell output. And there you go. Now we have a very simple application where a button click will trigger something to be printed in the Jupyter notebook. More sophisticated widgets can be used, such as a color picker, media viewers, and many more. All of the widgets available in the xWidgets or the JupyterWidgets framework are available in xWidgets. SQLite, Cling, and Python are not the only languages for which we made kernels using Xeus. Actually, there are quite a few others made by third parties that are part of the family. There is really one that I wanted to highlight here, which was built by Andrei Sotik. It's the LFortran kernel. Built upon LLVM, LFortran allows you to use the Fortran programming language interactively in the Jupyter Notebook or the Qt console. So I just included a screenshot of that in this slide. And there are quite a few others. Xeus Robot for the robot code, xeus-flit, the JuniperKernel, and xeus-calc are as many really powerful kernels that were built using this framework.
As Johan said, all you need to introduce a new language to the Jupyter ecosystem is to implement a kernel that speaks Jupyter's language. Xeus implements all the methods that we need to make that happen. It does the low-level communication between the Jupyter protocol and the language that you're implementing. So all we have to do is implement a few virtual methods, and we're gonna have a look at them next. So the kernel info request returns the information about the kernel, such as the name and the version of the kernel, and it's a mandatory method, you have to implement it. Complete request handles code completion. Is complete verifies if the code input is valid. Inspect request concerns documentation. It inspects the code and shows some useful information to the user. And the main method is execute request that it sends a message to the front end and asks the kernel to execute the code on behalf of the user. In the case of SQLite, we're using CPP SQLite to do this work. And to have a fully functional kernel, all you need is to implement two methods, the kernel info request and the execute request. And but Xeus goes way beyond that in customization. And one extension point is the server component. And Johan will show you more about it next.
Thanks, Mariana. Everybody should be now convinced that writing a kernel with Xeus is really super easy. Okay, let's now dive into another component of Xeus, which is the server. So here you can see the architecture diagram again, just as a reminder. Remember that the server is the low-level communication layer of the kernel. The kernel communicates with the client through 5 different sockets. The first one is the heartbeat, which is responsible for telling the client that the kernel is still alive. This is a really common pattern in middleware. Another socket used for communicating with the client is IOPub. This socket is meant to publish results after an execute request. So after code is executed or after you ask for code completion, for inspection, or whatever. So having this dedicated socket allows other clients to register themselves to the kernel and be aware of what is happening in this kernel. Then we have the shell socket. So this one is used for sending other requests from the client to the kernel. The control socket is similar to the shell socket but with higher priority, meaning messages sent on this socket will be processed before those sent on the shell. This behavior has changed recently, but we will get back to that later. And the last socket is the SDIN used by the kernel to ask input to the client. The default concurrency model in Xeus is run by 3 threads. The first one is for running the heartbeat. Another one is dedicated to IOPub. And the last one, which is usually the main thread, is used to call both the shell and the control socket. Xeus provides 2 additional concurrency models. The difference with the first one is that the control and the shell are polled by different threads. So in one of those models, the control is polled by the main thread, while in the other one is the shell that is polled by the main thread. In addition to these models provided by Xeus, you can also implement your own. This is typically what the SlicerJupyter project does, where the server is based on the Qt event loop. One of the motivations for having these different concurrency models was the debugger, because you may want to stop the workflow on the shell because you hit a breakpoint, for instance, but you need to be able to continue processing messages on the control channel. So this leads us to the last part of this talk, which is the debugger. Implementing support for debugging in Jupyter actually required more than just writing code. First, we had to augment the Jupyter protocol. What we did is we wrapped the debug adapter protocol into new Jupyter messages. Then we had to implement new messages specific to the interactive workflow of Jupyter. Basically, the code just lives in the kernel. It is not loaded from a file, and you need to give a debugger a mean to find this code. The last thing was clean separation between the shell and the control socket. So now the shell is responsible for processing execute requests, completion requests, inspection, and so on, while the control socket is responsible for processing messages relative to the state of the kernel or to the debugger. I won't spoil more. If you want to get more details, you can watch the talk Visual Debugger in Jupyter by Afshin Taylor-Darian, Jeremy Tulou, and myself. So what's next for Xeus? First, Xeus Robot, a JupyterKernel for the robot framework. The robot framework is an open source automation framework used for test automation and robotics process automation. We also want to provide a better support for magic in Xeus. Although we already implement a lot of magics, some of them are still missing, and we want to reach full parity with JupyterKernel. We also want to provide a debugger for the C++ kernel.